Download this code from codegive.com, link in the description below. OK, let's dive into the reservoir sampling algorithm. I'll provide a comprehensive tutorial with explanations, variations, and code examples in Python. Introduction to reservoir sampling. Reservoir sampling is a family of randomized algorithms for randomly choosing a sample of k items from a list of n items in a single pass, where n is unknown or too large to fit in memory. The key characteristic is that you only get to see each item once in a sequential stream. The goal is to ensure that each item has an equal probability of being included in the final sample, regardless of its position in the stream. Why is reservoir sampling useful? Streaming data. When you're dealing with streams of data where you don't know the total size in advance, example network traffic, search engine queries, sensor readings, reservoir sampling allows you to maintain a representative sample without having to store the entire stream. Large datasets. When the dataset is too large to fit in memory, reservoir sampling can be used to select a smaller, representative sample that does fit in memory for analysis, modeling, or visualization. Unknown size. Even if the total size is known but the data arrives sequentially, reservoir sampling provides a simple and efficient way to sample uniformly. The basic algorithm R. The most common reservoir sampling algorithm is often called algorithm R. Here's how it works. 1. Initialization. Fill the reservoir, the sample, with the first k items from the stream. 2. Iteration. For each subsequent item I, where ik. Generate a random integer j between 0 and I, 1, inclusive. If j is less than k, replace the item at index j in the reservoir with the current item I. Intuition. The core idea is to maintain equal probability of selection for each item. Initially, the first k items have a probability of 1 of being in the reservoir. As we process more items, we simulate the probability of each existing item being replaced by a new item. Proof of uniform probability. Let's outline a simple proof that, after processing n items, each item has a probability of k/n of being in the reservoir. For the first k items. When n equals k, each of the first k items is definitely in the reservoir. Probability is 1 equals k/k. For items k plus 1 to n. We'll use induction. Assume that after processing n1 items, each item has a probability of k/n1 of being in the reservoir. Consider an item x that was among the first k items. The probability that x is still in the reservoir after processing the nth item is. Consider the nth item. It has a probability of k/n of being selected to replace an item in the reservoir. Therefore, by induction, each item has a probability of k/n of being in the reservoir after processing n items. Python code example. Explanation of the code. 1. Reservoir _sampling, stream, k, function *. Takes an stream, an iterable of data, and k, the sample size, as input. Initializes an empty list reservoir to store the sampled items. 2. Filling the reservoir *. The for loop iterates through the stream. The if ik condition fills the reservoir with the first k elements of the stream. 3. Replacement logic *. Else for each item after the first k, a random integer j is generated between 0 and the current index I, inclusive. This is the crucial step. If jk. If the random index j is less than k, it means we've decided to replace an item in the reservoir. The item at index j in the reservoir is replaced with the current item from the stream. 4. Return the reservoir *. Asterisk after processing all items in the stream, the function returns the reservoir, which contains the sampled k items. 5 example usage asterisk. Asterisk the if underscore underscore name underscore underscore equals equals underscore underscore main underscore underscore colon block demonstrates how to use the function. Asterisk it creates a data underscore stream, a sequence of numbers. Asterisk it sets the desired sample underscore size. Asterisk it calls reservoir underscore sampling to get the sample. Asterisk it prints the resulting sample. Variations and optimizations. 1 algorithm L, for known stream length. If you know the length n of the stream before you start processing it, you can optimize the algorithm slightly. Instead of generating a random number in each iteration, you can pre-compute the indices of the items to include in the reservoir. This can improve performance in some cases, especially if generating random numbers is expensive. However, this optimization relies on knowing n in advance. 2 weighted reservoir sampling asterisk in some scenarios, you might want to assign different weights to items in the stream, giving some items a higher probability of being selected. Weighted reservoir sampling algorithms exist to handle these cases. 3 space optimization, when items are large. If the items in the stream are very large and copying them is expensive, you can store indices in the reservoir instead of the actual items. After the algorithm finishes, you can retrieve the actual items from the original stream using the stored indices. This avoids copying large objects repeatedly. 4 parallel reservoir sampling asterisk for very large streams, you can divide the stream into multiple substreams and run reservoir sampling in parallel on each substream. Then, you can merge the resulting reservoirs using another round of reservoir sampling. This approach is suitable for distributed processing. More advanced code example, index-based with generator. This example demonstrates using a generator for the stream, which is very memory efficient for large data sets, and using indices to avoid copying large objects. Explanation of the advanced example asterisk. Asterisk index underscore reservoir underscore sampling, stream underscore generator, k, asterisk. Asterisk takes a stream underscore generator, a Python generator, as input, which yields items from the stream one at a time. This is crucial for memory efficiency because we don't need to load the entire stream into memory. Asterisk maintains reservoir underscore indices to store the indices of the selected items from the original stream. Asterisk maintains sampled underscore items to store the actual sampled items. This list is directly built with the items generated by the generator to improve speed by not accessing items again after the generation. Asterisk count tracks the number of items processed. Asterisk generator function asterisk. Asterisk data underscore generator, n, is a simple generator that yields strings. In a real application, this could be reading data from a file, a network socket, or some other streaming source. Asterisk usage asterisk. Asterisk creates a generator using data underscore generator, stream underscore length. Asterisk calls index underscore reservoir underscore sampling to get the sample. Asterisk prints the indices and items, to show what was generated. When to use reservoir sampling. Asterisk you have a streaming dataset asterisk the data arrives sequentially, and you can't store the entire dataset in memory. Asterisk you don't know the size of the dataset in advance asterisk reservoir sampling works even if you don't know the total number of items. Asterisk you need a uniform random sample asterisk you want each item to have an equal probability of being included in the sample. Asterisk memory constraints are a concern asterisk reservoir sampling allows you to maintain a fixed size sample without storing the entire dataset. Summary. Reservoir sampling is a powerful and versatile algorithm for randomly sampling from streams of data. It's efficient, easy to implement, and well suited for a variety of applications where memory constraints are a concern or the data size is unknown. Remember to choose the variant that best suits your specific needs, considering factors like the availability of the stream length, the size of the items, and the possibility of parallel processing.